Hello. Today we will discuss Young's single slit experiment. And you will find that the single slit experiment setup is not that different from the two slit case, except that this time there's just one single slit. In the double slit case, when light passes through two slits that are very closely spaced, the slits act as sources of wavelets that pass over each other and interfere constructively and destructively, so that you end up with an interference fringe pattern. In both cases, it is important to realize that light diffracts. It's the diffraction of light that leads to the interference. And as I mentioned in the first video, diffraction of light is not very easy to see in everyday activities because the wavelength of light is so much smaller than the dimensions of everyday objects. But if you consider, let's say, sound waves or radio waves whose wavelengths are about similar to everyday objects, the dimensions of everyday objects, you can easily see the diffraction or experience the diffraction with these waves. Let's consider sound as an example. You recall from college physics 1 that the audible range goes from about 20 hertz to 20,000 hertz. So this is the range of frequencies that the human ear can hear. So let's pick out a typical typical frequency to do a calculation with. Suppose that we consider the case where the frequency is 1,000 hertz. Then, of course, the wavelength corresponding to this will be given by the speed of sound divided by the frequency. The speed of sound for a 20 degrees Celsius day is about 343 meters per second. And if we divide this by 1,000 hertz, then we get a wavelength of the order of, say, 0.34 meters, i.e. about 1/3 of a meter. So if a meter is about this much, so you can imagine 1/3 of a meter. And the point I'm making is that everyday apertures, everyday space in between objects is about this size. So it's possible, very easy for sound waves to diffract. As an example, you can easily hear when somebody is talking to you, when you cannot see them, they're not in your direct line of sight. If you are around a corner, you can still hear them. The reason you can hear them is because sound waves easily diffract. Or take the case of radio waves. Let's consider our own radio station, which has a frequency of 90.5 megahertz. And of course, for this, the wavelength will be given by the speed of light divided by the frequency. So this is 3 × 10⁸ divided by 90.5 × 10⁶. So approximately this works out to be about, let's say, 3 meters. Okay, so if you look at, say, two adjacent buildings from the top, say here, so this is drawing the homes from the top. The spacing between them, so if radio waves were to arrive as wavefronts, then they can easily diffract because the dimension here is about the same as the wavelength of the radio wave that came in. And so, once again, you don't have to necessarily be in the line of sight of the radio transmitting antenna before you can get a signal, okay? Radio waves diffract quite easily. Today, we shall look at this diffraction for the case of a single slit experiment. There's a single slit. Consider the following. Suppose that you have a piece of card, and in this card you cut a rectangular hole whose width is D. We shall use uppercase D to represent the width. And suppose that you then place a viewing screen somewhere behind it. Then let's suppose that you shine light on the hole in the paper. Clearly, if the light goes through it, you will see just a rectangle of light, a rectangle of illumination on the card. Okay? If you were to scan across this illumination on the paper, you will obtain something like this. In other words, there is nothing here, this is 0, and then it suddenly rises up to some bright level across the width, and then it drops back to 0. So this is it here. Where this here is about the same uppercase D. However, if you reduce the size of this width here, so the first case that I discussed here, this is the case where size D is much, much greater than the wavelength of the incoming light. But if you reduce this somewhat, then this here becomes, not only does it become narrower, but then also the edges are not so sharply defined, so you'll end up with something like this. Okay, whereas before this was pretty sharp, this is no longer that sharp. If you keep reducing the size until you have a situation where the size D is not much larger than the wavelength of the incoming light, you see something very totally different. And probably the best thing to do now is to draw out what you would see. And this is the single slit diffraction pattern that we're going to describe. So now I'm going to draw the card looking from the side. This is the width of the slit. And I'm suggesting that if you shine light onto the slit assembly, this is what you would see. Most of the intensity of the incoming light will be concentrated right on this midline, which we shall call theta equal to 0 degrees. But it will be much broader than the size D. It will be something like this. It will be wider. Okay. Most of the intensity is contained in this central bright portion. And then bordering the central bright portion will be one fringe here, which is not anywhere as bright as the central one, and then there's another one probably somewhere here. And then there is a much weaker one here, and a much weaker here. And it goes on for a while. It very quickly dies out though. But this pattern here is very different from what we observed with the double slit experiment. And I'll indicate this by drawing for you the brightness as a function, the brightness versus space. So let's say the brightest portion will be on the center here. This here is completely dark. So you would obtain something like this. It goes up. And then you may probably have other ones beyond it. This is very different from what we discussed under Young's double slit experiment. This here, to distinguish it from the interference fringe pattern for the double slit experiment, is called simply a diffraction pattern. But understand that it's still a combination of diffraction and interference that leads to this pattern. At this stage, you might ask the question, well, how is it that a single slit can produce an interference pattern? This question was answered sometime in the 17th century by a Danish scientist called Christian Huygens. I'm not sure that I'm pronouncing it right because there's a proper Dutch pronunciation, but Huygens will do fine for us. And he suggested the following: that every point on a wave front can be considered a source of wavelets that propagate forward with the same wavelength and at the same speed as the original wave. So, for example, imagine a single wavelength light, a monochromatic light propagating forward. And these are the wave fronts. Well, he's suggesting that this wavefront here can be obtained by the following analysis. Imagine that this point here is a source of wavelets that move forward with the same wavelength. And then this does so with the same wavelength and so on. So that the next wavefront, this wavefront, is simply a tangent or an envelope. It's a tangent to the surfaces of the wavelets or an envelope of the wavelets. And this is how you can predict the position of the next wavefront from the previous wavefront. So this is called Huygens Principle. Essentially says that every point on the wavefront acts as a source of wavelets that propagate forward with the same wavelength and at the same speed. Of the original wave. And that the next wavefront can simply be constructed by drawing the envelope of all these wavelets. So the key point here is that every point on a wavefront can be considered a source of wavelets. And this is how points along this wavefront here produce their own diffraction that eventually ends up passing over each other and producing this interference pattern. So we're going to now look at the details. We're going to look at how it is that we can get the central maximum and under what condition do we get this first dark, second dark, and third dark. So the analysis here is going to be a little different from what we did for the double slit case. Here we will focus not on the bright fringes but on the dark fringes. So this is the first dark. This is the second dark. This is the third dark, and so on. And once again, this is symmetric. So this is first dark, second, third, and so on. Okay. So to do the details, let's begin by considering the central maximum. The central maximum, this is also very often called the diffraction maximum. can simply call it the central maximum. So, and that occurs along the line that we have called theta equal to 0. So I'm going to exaggerate the size of the slit to make this discussion clear. So this here is our slit assembly. The distance from here to there, this is the width of the slit, we shall call uppercase D. If we draw the midline, this is the angle theta equal to 0. So let's place a screen here, such that our screen is a distance L, using the same language from the double slit discussion. It's easier to, say, pick the following points with which we shall construct our wavelengths. We shall pick this point, the midpoint here, and the midpoint here, and the midpoint here. So let's call this source 1, 2, 3, 4, 5. And as I said in the very first discussion, we can either represent the wave that's propagating forward with these wave fronts, or we can simply draw a wave like this that's moving forward. Okay? So from point 1, we shall have a wave that's moving forward all the way. Let's draw a line to shorten this discussion, all the way to the screen. And similarly, from 2, we shall draw our wave going all the way, and from 3, and from 4, and from 5. Okay. But as you can see, all these waves, waves 1, 2, 3, 4, and 5, or whatever other wave that you can think of here, travel the same distance. So if they all begun on a crest, they will end up on a crest. And because they all end up with a crest, they interfere constructively, which is why the central portion is a maximum. Okay? They travel the same distance. Let me write it out here. So all waves travel the same distance. Therefore, they are always in phase. And hence, we shall obtain a maximum. Okay? All right. So that's easy enough. Now let's consider the first dark and the second dark and the third dark, and write a very simple equation to describe the pattern. So we shall consider first the first minimum, which occurs at some angle theta, which is not equal to 0. Okay. All right. So here is the slit. And here is our screen. The distance here is L as before. This is the midpoint here. Now we're considering a different angle. So we're going to draw a line that goes up like this. So from the midpoint here, let's draw a wave that's propagating to, let's say, this point here. Now, the distance L is so much larger than D. So we can draw these lines as though they were parallel, as though they were parallel waves going to create a destructive interference here. So This is, once again, this is 0.1, this is 0.2, this is 3, this is 4, this is 5. And so these waves will travel as follows. Permit me, my lines have to be parallel. All right, and then this will go up like that. Okay. But now you can see that since effectively when we draw this, we're drawing all of these to the same point. And it's just that okay, let's do this. This is actually going to the same point to the right. And it is for this approximation that we're assuming that the waves are parallel to each other. But in fact, in reality, they are not, because if they are traveling to the same point, then they must be doing something like this, right? But just to make the mathematics easier, we're going to assume that the rays are traveling parallel to each other. And in that case, if you pick ray 1 and ray 2, wave 1 and wave 2, you will find that there's a path difference, this little path difference between them. Okay? If you consider wave 2 and 4, there's a similar path difference. This little path difference here. And similarly, for 3 and 5, there will be the same path difference. The path difference we can calculate very easily, because it's just 1/2, this distance from here to there is just 1/2 of the original width. So this will be d over 2. This distance here is d over 2. Since this angle here is theta, this angle here must also be theta. So we have this right angle triangle whose opposite side to the angle theta is the path difference. And so you can see that the path difference is simply d over 2 times sine theta. And you recall also that in order to obtain a minimum, you have to have two waves that cancel each other out. The way two waves cancel each other completely is if one is at a crest and the other one is a trough. That is to say, if the path difference is 1/2 of a wavelength. So if we set d over 2 sine theta equal lambda over 2, then we obtain our very first minimum. Well, since we have 2 on both sides, let's multiply the equation by 2, and then we obtain d sine theta is just lambda, and that is the condition for the first minimum. Okay, let's do another one for the second minimum, and you'll see that there will be a pattern, and we can then just make a conclusion from these two analyses. So now we consider the second minimum, occurring at some angle theta that is steeper than the angle that we considered for the first minimum. So this will be a steeper angle. It's different. So you can call it theta prime or whatever. Okay. Asterisk. Okay. So once again, here is our slit assembly, and our screen is somewhere here. This is the distance, uppercase D. This is the width of the slit. This time, we shall divide our width into 8 parts. So we shall have wave 1, 2, 3, 4, 5, 6, 7, 8. Let me do this properly. So this here is the midpoint. So this here is 2, 3, 4, 5, 6, 7, 8, 9. Okay. And then we draw the waves that are traveling to some steeper angle. They're going all the way to some point. Don't forget, each of these is a wave that's traveling forward. But now, if we consider waves 1 and 3, there will be a certain path difference here. Given that this angle is theta, we can easily calculate the path difference. And once again, if this path difference is equal to 1/2 of the wavelength of light, then we're going to end up with a destructive interference, and for that reason we shall end up with a minimum. If you consider waves 1 and 3, you can as well consider waves 2 and 4, or 3 and 5, 4 and 6, and so on. Or arbitrarily, you can pick any point, and for every point that you pick, there will be a corresponding point above it which will create the conditions that we're describing here. So in this case, because we're divided this whole thing into 8 parts, the distance between 1 and 3 is 1/4 of d. So the path difference this time will be given by 1/4 of d times sine theta. That's this little distance here. This is the path difference between waves 1 and 3. And I'm arguing that if this is equal to lambda over 2, then we should expect a minimum. We should expect a cancellation. So the condition for the second minimum is that d over 4 sine theta should be lambda over 2. If we multiply both sides by 4, then we obtain d sine theta is 2 lambda. And this here will be the condition for the second minimum. So you can see a pattern developing here. So for the first minimum, we have 1 in front of lambda. For the second minimum, we have 2 in front of the wavelength lambda. So if we continue this analysis, you can easily see that d sine theta will be 3 lambda for the third minimum, and so on. So for this reason, we can generalize and write a simple statement to describe everything that we've done so far. So for the single slit experiment, the equation that describes the location of the minima or the dark point is d sine theta is m lambda, where m takes on the values. This time we begin at n equal to 1 and 2 and 3 and 4 and so on. In this equation here, d stands for the width of the single slit. M is as defined, and of course lambda is the wavelength of light that has been used for this experiment. This is a simple equation whose application we must do carefully, because we must not confuse it with the double slit equation. And before I move on, before we do any problem, I'm going to just summarize the very important differences between the single slit experiment and the double slit experiment, so that we are very careful and do not make unnecessary mistakes. For the double slit experiment, we use d, little d, to represent the separation between two slits. Single slit, we use uppercase D. This is the width of the slit. Some textbooks use lowercase a, little a, here to represent the width. Also, here, M goes from 0 to 1, 2, 3, 4, and so on. This is very different. Here, M starts at 1. Please be careful. And whereas we are describing bright and dark here, here we are describing only the dark or the minima. Okay? So pay attention to these differences. So we'll just do one problem, and that should be the end of the discussion. But the homework problems, the homework problems are very similar to the OpenStax practice problems. So I suggest that you look at those before you look at the homework problems. So I'm gonna just quickly go through homework 10. And this is question 8. Which says helium neon laser light of wavelength 779.2 nanometers is sent through a 0.169 millimeter wide single slit. Question: what is the width of the central maximum? What is the width of the central maximum on a screen that is 0.54 meters from the slit? Okay, well, let's draw a diagram to illustrate what's going on here. So we have a single wavelength or monochromatic light that comes here, passes through a slit whose size is given to us. So this here is our D, this is our lambda, and this is our screen, and the screen is a distance L equal to 0.54 meters. This is 0.169 millimeters. The central maximum will form like that. And then, of course, this is the first minimum, and then there's that. Okay. This here is the width. When the question says the width of the central maximum, they mean the distance from here to there. This is the width of the central maximum. If you had the maximum, if you do this with a laser light, you would see that the maximum stretches all the way from here to there. Okay, so this is the entire width. But as you can see, if we call this distance here y, then the width will simply be twice that, 2y. And this angle, theta, corresponds to the angle for the first minimum. So we shall use our equation and set m equal to 1. So we already have the equation here. So d is 0.169 millimeters. Do not forget to change all these numbers to SI units. So we shall have 0.169 10 to the negative 3 times sine theta should equal, m is 1 in this case, because it's the very first minimum. So 1 times the wavelength is 779.2 nanometers 10 to the negative 9. And so we can easily solve for the angle sine theta. So we can solve for sine theta, I mean. So sine theta will be 779.2 10 to the negative 9. And then we shall divide this by 0.169 10 to the negative 3. Now, as you can see, this is going to be a very small angle, which suggests that the small angle approximation ought to be applicable. So we have 779.2, and we shall divide this by 0.169 x to the negative 3, and that gives us 4.6106 10 to the negative 3, for which the sine inverse gives us theta is 0.26417 degrees. A very small angle. So the small angle approximation works very well here. So we shall set, we can use the small angle approximation. And we did this in the last video. We can write dy over L is equal to m lambda. M is 1, so equal to lambda, from which we can solve for y as lambda L divided by d. Okay? The width is 2 times y, which becomes 2 lambda L divided by d. So I leave the rest for you to complete, but this is how you would approach a problem like this. Okay? All right. I'm now going to discuss the very last part of chapter 27. The last part of chapter 27 looks at thin film interference. Thin film interference. We are all familiar with the rainbow colors of very thin soap bubbles and oil slicks. These come from constructive interference of light, as simple as that. When light, we learned in the last video, when light goes from one medium to another medium, it diffracts. The diffraction causes a dispersion of the light, and if the dispersed light interferes with itself, you get constructive interference, and you can see very brilliant colors. So I'm going to use the example of an oil slick to show you what would happen. So suppose this here is a very smooth surface of water, and this here is some thickness of oil. You know what, let's draw this larger so you can see, even though we're really working with a very thin film of oil, but it's okay. And so this is air, this is oil, and this is some water. let's say that the thickness of the oil is little t. And here's what happens. So imagine that light hits the surface, the interface between air and oil, like so. And as we normally do, we shall erect our normal here. And you remember that blue bends best. So our blue light will bend like so, and our red will bend like that less. Okay, here's the red. But of course, when the light hits the surface here, a portion of it is reflected. You remember this from an earlier chapter. So let's begin the discussion by looking only at the blue component of the light. So the blue light comes in here, part of the white light is blue, and then it reflects here. Part of the light that went into the light that went into the oil was diffracted. When it hits this boundary, part of it will reflect back up here, and then it will come out. So if you set your eye here, then let's call this ray 1 and this ray 2. Let's call this ray 2. Let's call this point here A, this B, and C. It is possible for ray 1 and 2 to interfere. It is possible, therefore, to get constructive interference if the part of the wave that traveled this extra distance, A, B, C, does so in such a way that when it comes here, let's imagine that it was a crest going in. If the path A, B, C is such that when the wave has arrived here, it's now a crest, then when this enters the eye, crest meets crest, they are in phase. You'll get a constructive interference. And therefore, the region AC will appear very bright on account of constructive interference. So, if the path A, B, C is a whole number times the wavelength in oil, because after all, this path A, B, C is in oil. But if A, B, C is m lambda prime, then we will get a bright, the blue will shine bright. So let's just do this for the blue. And by the way, we're looking kind of perpendicularly, so approximately the path A, B, C is about 2 times t. So let's say that A, B, C is approximately 2t. Then our equation becomes 2t is m lambda prime, where lambda prime is the wavelength in oil. Okay? Now, the index of refraction that we discussed earlier is as follows. The index of refraction, let's do it for blue light. Index of refraction is the speed of light in vacuum divided by the speed of light, this time in oil. You recall also that the speed of light can be written as a product of the wavelength and the frequency. So this here is the wavelength of blue light, and this is the frequency of blue light. And then we divide this by in oil, the wavelength is different. Now it's lambda prime. But the frequency does not change. The frequency will not change. So this is something that you're learning today. If light were to go from vacuum or air into some other medium, the frequency will not change. The wavelength will change, and therefore the speed of the wave changes. but the frequency remains the same. So FB is the same FB here, so they cancel out, and we end up with NB is just lambda B over lambda prime. So we can solve for lambda prime as follows. Lambda prime then becomes simply lambda B divided by the index of refraction. So our equation then becomes 2t is simply m lambda prime, and instead of lambda prime I shall now write lambda b over nb. Lambda b over nb, and if you can finish this by writing 2t nb is m lambda b. Done. In this equation, T stands for the thickness of the oil slick. NB is the index of refraction. M is the normal order 1, 2, 3, and so on. Oh, let's say that. 2, 3, 4. And lambda B is the usual wavelength, the wavelength of blue light. Everything that we've said here applies to every other color component of the incoming white light. So you can write this expression for all the other components. But the point is that you will see a very bright portion between A and C for blue light if this condition is satisfied for blue light. And at a slightly different viewing angle, this condition is satisfied for some other color. This is what gives a thin film its brilliant rainbow colors. The analysis is very similar for a soap film. There is one key detail that I left out, and let me just mention it, even though it does not affect our analysis. The index of refraction of air is less than that of oil, and the index of refraction of oil is less than water. Whenever light reflects going from less to greater, there will be a phase change. Okay, the light, if it went in as a crest, turns down to a trough. It's a 180-degree phase change. But a similar thing happens when you go from oil to water. So those two effects cancel out, essentially, which is why I did not include them in the discussion. But the point is that this equation applies. And since T is very small, of the order of not much larger than the wavelength, we can see constructive interference. And so we see very bright colors. This essentially is the end of the discussion of the wave properties of light. I have a very small piece of homework assignment for you, which is the following. I want you to answer the question, why is it that the sky is blue? When you look up at the sky, not looking directly at the sun, number one, that's dangerous, and so don't do it. Number two, I'm not interested in the color of the sun or sunlight. Why is it that the sky is blue? Okay. And in addition to this question, why is it that at sunset, the light, if you look at the sun when it's setting, the light you see is orange, sometimes it's golden, and sometimes it's red. Why is that? I can tell you right here that your answer to part A is the same phenomenon. So look into it and let me know what you come up with. Thank you.